when you speak about this algorithm, does it only take the upstairs partition?
Just the upstairs partition, nothing else about the sheaf.
Okay. Okay. So the sheaves are somehow lurking in the background, but do not enter the computations in any way.
Right. But of course, this partition can be much worse than what you might have a much more efficient partition downstairs, which you don't compute. But there you can say something constructive about the sheet, though, that if you also have a bound on the homologies of the fibers, then you can bound the homology of the fibers of the direct image singly exponentially in this sense, yes.
And for different sheaves, do you get different algorithms? Or is it
No, it just depends on the partition, because the algorithm does not look at the sheaf.
Uh-huh. So what you are saying then is that the partition, this, in addition to this push forward thing for constructible sheaves, you get something which produces you a good partition downstairs, independently of what sheaf you started with, but only depending on a good partition for
Only
that
good
sheaf.
partition, yes.
Yeah, but don't forget that
Uh-huh.
the partition means that the sheaves are constant on those, so that's
Yeah,
why there's nothing happening
sheaf.
much on
Yeah.
those.
Partition basically is a sheaf for all intents and purposes.
That's not obvious to me, but okay. Mhm.
And if you have the partition bound in the partition, bound on the one side. So I consider this as analog of Tarski-Seidenberg. It gives you a little bit more. If you take the constant partition upstairs, for example, it gives you a little bit, this partition is going to be finer than, for example, in the quadratic discriminant case, this partition will give you at least the partition into 3 parts. Well, Tarski-Seidenberg will. And by the way, it might look like it's not a big deal to, if you have a semi-algebraic, locally closed semi-algebraic set and its complement, then you want to say that you have a finite partition which has the boundary thrown in. But to compute the boundary of a semi-algebraic set, or for that matter the interior or frontier, any such thing, it's not trivial. In fact, it requires algorithmically the full strength of quantifier elimination. So if I give you a semi-algebraic set, you want to compute its closure, for example, we know no other way than to use quantifier elimination. So that's just a side comment. So I cannot talk a little bit, I cannot really give much details on the proof, but I'll say that it depends on several ideas that have been successively introduced in algorithmic semi-algebraic geometry. But the key idea goes back to my paper with Kolya Vorobjov, and there we were proving that if you have a semi-algebraic maps, in fact we are proving it for more general categories for quinomials or Fathian sets and so on, but let's restrict ourselves to semi-algebraic sets. And I said that if you want to bound the number of homeomorphism types of the fibers, then the best we can do is doubly exponential. But if you want to do less, and you want to bound the number of homotopy classes of fibers, which is at most the number of homeomorphism types, but could be much smaller, then we proved single exponential bounds on the number of homotopy classes of fibers of a map. And making this proof effective, it plays a very key role in this algorithm.
Would, for instance, this result follow from the previous result if you take the constant, the global constancy or something? Or?
Yes, it
Yeah.
would follow from the previous result. But this is more, yeah, so that was the start, this was our starting point. And then there are some technical things that we need in these new things, like for example, if you have a collection of polynomials, then it's possible to obtain single exponential size coverings of in space such that each element of the covering is a contractible set, and the contractibility comes in our case because if a sheaf is locally constant, it does not tell you that it's a constant sheaf, but if it's locally constant or contractible, then it's actually a constant sheaf. That plays a role in our proof. And then there are typical arguments in this business of using infinitesimals to thicken and shrink and spectral sequences and the basic thing about the proper phase change. But that's, so there are several ingredients, all of which are well studied, but you have to use them properly. Okay, so that's my quantitative part. And in the time remaining, I'll make a little bit more speculative complexity theoretic. And that, you'll see the reason why I was pedantic about these functors and adjointness and so on. So I want to talk a little bit about the Bloom-Schultz-Smale complexity classes. And so I'll probably I'll just say something. So I want to define it in a little bit, might be non-standard way. So we talk about S, strict S to the category of sequences of semi-algebraic sets, where M of n is some increasing function. So any such sequence is an object of this category. And in Bloom-Schultz-Smale sense, such a sequence is in P over R. In the class P over R, if there exists a Bloom-Schultz-Smale machine, which is some kind of a real computer, that recognizes L in polynomial time. Meaning, given a n and a Sn and a point in Rn, it can decide whether x is in Sn or not in polynomial many steps. So this class, from more or less again from the definition, is this polynomial class is obviously stable under taking products, unions, intersections, and also pullbacks. And the famous P versus NP or Po NP question is it stable under these other two functors? So we can say that these other functors, they induce a natural way some endofunctors of S. And there are these adjointness. The following inclusions are obvious, that P is this and that. And so for historical reasons, it's traditional to denote, I think, because of non-determinism, this n sense of that NP as this and co-NP as that. And then there's a notion of a whole hierarchy where you compose this endofunctors like this. That's called the polynomial hierarchy of the reals. And what is believed to be true is that this is a proper hierarchy, that P is not equal to NP or co-NP, or for that matter, the polynomial hierarchy is not the same as P. That's the famous question. So we can try to mimic this because we have been talking about semi-algebraic sets and maps and complexity for classes of sheaves. So we should define some class of simple sets of sequences. And so I don't want to give you the detail because, so there is a subordinate partition and then there's the homology of these talks. So we call a set to be in the simple class if you can, so this partition is allowed to have exponentially many pieces, but you should be able to locate a point efficiently. So there is technical meaning to this statement that point location can be done efficiently. And you should be able to, given a point, compute these dimensions of this talk in polynomial terms whenever I say efficiently. So this is the technical definition, let's skip, because that's all that it says. And then you could ask, okay, so this is also part of the technical definition. So like it's strictly generalization because if you take the constant sheaf on a sequence in P in the Bloom-Schultz-Smale sense, then this would be simple. But there are other non-trivial examples of sheaves in P, which I don't want to. So what we can prove quite easily is this class is stable, just like the Bloom-Schuh-Smale, under some simple operations for the derived category. It's also stable under the inverse, just like P is stable under the inverse. But what about the direct image functor? And that gives rise to a P versus NP question for sheaves. So again, you have these inclusions. But the question is, does this class, so we can define a class of sheaves, except that now the existential and the universal quantifiers become one class here. Because I'm just looking at the class of sheaves obtained as derived images of derived images of these simple sheaves in P. And so we have the notion of a polynomial hierarchy. I'm going very fast, I'm sorry because I'm out of time here, but we can conjecture just like P not equal to NP whether these two classes are not the same. There is a small theorem here that in the Bloom-Schuh-Smale sense, if you can prove that P not equal to NP, then this would imply that this is not equal to that. But so this question should be easier to resolve if you believe that P not equal to that. Okay, so might be. So, should I finish now? 5 minutes, okay. Okay, so let me also say something about topological complexity. So another aspect of real algebraic geometry has been, if you are given a semi-algebraic set with bound on the format of the formula defining it, like S polynomials, degree at most D, one can bound by a single exponential quantity like that the sum of the Betti numbers of X. So this kind of results goes back to all the way from the 40s to work of Olenek and Petrovsky, later Tom and Milne. So now that we have a notion of complexity of constructible sheaves, and constructible sheaves has hypercohomology, we generalize as the notion of cohomology for the constant sheaf. So we could ask effective bounds on the hypercohomology of constructible sheaves in terms of the complexity of the subordinate partitions and bound on the fibers. But I want to present this, so that can be done separately, but I want to present this in the context of this Bloom-Schuh-Smale complexity. So in the Bloom-Schuh-Smale complexity, we have sequences of semi-algebraic sets here. So suppose we have a sequence of semi-algebraic set in the class P. Then it's a consequence of these results of Olenek and Petrovsky that I mentioned before, that if you have one fixed sequence in P, then there exists a constant that depends on L on this sequence, such that the Betti numbers, now the ordinary Betti numbers of the set Sn grows at most singly exponentially in N. And this just follows from the Olenek-Petrovsky bound and the fact that it's very easy to see that if you have a sequence like that in P, then the degrees of the polynomials and the number that defines these sets Sn grows singly exponentially in N, just because in a polynomial time machine you cannot produce degrees. That's the consequence. You could think that, well, now this might be a tool to separate P from NP, right? Because if you can exhibit a language in NP where the growth of the Betti numbers is faster than singly exponential, then P would be separate from NP. Then you'd be a millionaire. Well, not quite, but because it's over real. Right? But unfortunately, this is not true because, in fact, if you take any language even in the polynomial hierarchy, then the same theorem is true. That the Betti numbers can grow at most singly exponentially. But the result that I want to present is that the same single exponential growth is also true sheaf theoretically in this. So if you have class sequence of constructible sheaves in this simple class, then according to the definition presented, then the hyperhomology of these sheaves can grow at most singly exponentially, and in fact, just like as before, that you cannot use this fact to separate P from this bigger class, because it's also true for things in polynomial. So there is this. So the thing that I want to stress is that just like in semi-algebraic case, you can bound effective bounds on the Berry numbers. Constructible sheaf case, if you put a certain measure of complexity, like I did for constructible sheaves, then you can also effectively bound the hyperhomology. Again, I probably skip this. So there is a shadow of constructible sheaf theory. If you take for your stocks just the Euler characteristic, then you get something called a constructible function. And then everything that, all this complexity theory that I've described can be done for such constructible functions rather than constructible sheaves, which is a simpler things to think about, because a constructible function is just a linear combination of characteristic functions of some finite number of semi-algebraic sets. So, and if you take the Euler characteristic of stocks of a constructible sheaves, then you get a constructible function, so they can define what does it mean for constructible functions to be in class P. And that theory is slightly more developed in the sense of some complete problems and so on. So let me just end with some open questions. So I think this is just the beginning. So there are other functors, particularly the inner home, and also what is related to it, and all the shrieks, especially upper shriek, and the Bardier duality has not been taken into account here, so there's a lot of, one can talk about these in this effective sense. Get rid of this properness assumption, which is a botheration, not just here in algebraic geometry, but also in complexity theory for various reasons. So, and might be more interesting from the point of view of logic is that there is some very suggestive things about adjointness, right? That the inverse is adjoint to the push forward. One is easy, one is hard. Same goes for sheaves, but then there are other classical adjoint functors like tensor home. And we know that the tensor is easy from the point of view of sheaves. I don't know about home, but might be this is another analog of a P versus NP type question. So that you have an adjoint pair of functors. So might be it has to do with preserving limits and colimits and things like that. That I think is speculative, but I think interesting. So there are applications of this in D-module theory, algebraic PDEs, and so on. Constructible functions. And then there are certain algebraic sets, semi-algebraic sets, that are very intimately related to constructible sheaves. So given a constructible sheaf, even a constant sheaf for semi-algebraic set, there is a particular subset of that lives in the cotangent space, which is a very special kind of subset, semi-algebraic subset, the conical Lagrangian is called the singular support. So this measures, keeps track of the locally of the directions in which there are topological changes. And it is true that if you have constructible sheaf, then the singular support is a semi-algebraic Lagrangian subset of the cotangent space. And this singular support is very important because, for example, in the connection with D modules, so there is this something called the Riemann-Hilbert functor correspondence that gives you a correspondence between constructible sheaves over complex numbers and regular holonomic D modules, which corresponds to certain overdetermined systems of linear PDEs. And so such linear PDEs, there is this characteristic variety, and on the constructible sheaf side, there is a singular support, and the characteristic variety is equal to the singular support under this correspondence. So I think it's quite interesting to study the complexity of this singular support in terms of the complexity measures defined that might help in even on the PD side. But all these things are speculative. So, okay, so.
More questions? Okay, thank you very much.